Section: Introduction. In this section, we discuss the recent advancements in visual generation, particularly in creating high-quality images and videos. One of the most complex tasks in this field is text-to-image generation, which requires a deep understanding of language and the ability to create intricate scenes. We categorize visual generation into two main approaches: diffusion models and autoregressive models. Diffusion models work by reversing the process of turning data into random noise, generating images through a continuous denoising method. In contrast, autoregressive models utilize the strengths of language models by converting images into discrete tokens and predicting these tokens in a sequence, which allows for image generation. However, autoregressive models struggle with high-resolution text-to-image synthesis, often producing lower-quality images compared to diffusion models. They also face inefficiencies due to the way they predict tokens, which can slow down the generation process. Recently, visual autoregressive modeling has introduced a new method called coarse-to-fine next-scale prediction, which shows better generalization and scaling than diffusion models while requiring fewer steps. Despite this, the discrete tokenization used in these models leads to significant errors, especially in high-resolution images, resulting in loss of detail and distortions. To address these issues, we propose a new approach called bitwise modeling, which replaces discrete tokens with bitwise tokens. Our framework includes three main components: a bitwise visual tokenizer, a bitwise infinite vocabulary classifier, and bitwise self-correction. By expanding the tokenizer's vocabulary to a massive size, we achieve reconstruction quality that surpasses previous models, yielding results comparable to continuous models. Our method, named Infinity, Bitwise Visual AutoRegressive Modeling, retains the advantages of speed and scaling while enhancing detail and quality in image generation. Infinity sets new benchmarks for autoregressive models and outperforms leading diffusion models on various text-to-image tasks. Notably, it improves scores on several benchmarks and reduces inference latency significantly. In summary, our contributions include the introduction of Infinity, which enhances the capabilities of discrete generative models and opens new avenues for the community. Infinity demonstrates the potential of scaling tokenizers and achieving high-quality image generation, while also ensuring fast inference speeds. In the related work section, we note that autoregressive models utilize discrete image tokenizers and next token prediction to generate images. However, existing methods face limitations due to quantization errors and the lack of advanced scaling. Recent models have attempted to improve performance in text-to-image and video synthesis, but our approach offers a significant advancement in quality and efficiency. Section Summary. In this section, we discuss the advancements in visual generation, particularly in text-to-image synthesis, highlighting the limitations of current autoregressive models due to quantization errors and reconstruction quality. We introduce our novel approach, Infinity, Bitwise Visual AutoRegressive Modeling, which utilizes bitwise tokens to enhance scaling and detail representation, achieving superior image generation quality and faster inference compared to existing models. Section: Diffusion Models. In this section, we discuss diffusion models, which have rapidly evolved in various ways. We have focused on improving denoising learning methods and sampling efficiency to create high-quality images. Notably, latent diffusion models were the first to model in latent space instead of pixel space. Recently, we have scaled up variational autoencoders, VAEs, to enhance representation in latent space. Models like DIT and UVIT have adopted a more scalable approach to diffusion, yielding better results. As a result, the DIT architecture has become common in mainstream text-to-image diffusion models. Next, we explore scaling models. We observe that scaling laws in autoregressive language models indicate a power law relationship among model size, dataset size, and computational resources, which helps us predict the performance of larger models. This understanding allows for efficient resource allocation and continuous improvements without reaching a saturation point. We also introduce visual autoregressive modeling. In this approach, we use a visual tokenizer for image synthesis. During training, we work with a sample that includes a text prompt and a corresponding ground truth image. Our visual tokenizer encodes the image into a feature map and then quantizes it into multiple residual maps of increasing resolution. We can gradually approximate the continuous feature based on these residuals. The model learns to predict the next scale's residuals based on previous predictions and the text input in an autoregressive manner. The autoregressive likelihood is defined using text embeddings, which guide the predictions through a cross-attention mechanism. We note that increasing the vocabulary size can significantly enhance reconstruction and generation quality. However, simply enlarging the vocabulary in existing tokenizers can lead to higher memory and computational costs. To tackle this, we propose a new bitwise multi-scale residual quantizer that reduces memory usage, allowing for the training of very large vocabularies. In our bitwise multi-scale residual quantizer, we replace the original vector quantizer with a dimension-independent version. We consider two candidates for this quantizer. For each scale, we quantize the input continuous residual vector into binary output. To promote effective codebook usage, we introduce an entropy penalty. However, calculating the distribution of the quantized output can be computationally expensive. We face challenges with memory when the codebook dimension is large. In contrast, our proposed method simplifies the entropy penalty calculation, significantly reducing computational complexity and avoiding memory issues, even with large codebook sizes. Section Summary. In this section, we discuss advancements in diffusion models, particularly the introduction of latent diffusion models that operate in latent space for improved image generation, and the implementation of scalable architectures like DIT and UVIT. We also explore the development of a bitwise multi-scale residual quantizer that enhances vocabulary size for better image synthesis while minimizing memory and computational costs. Section: Infinite Vocabulary Classifier. In this section, we introduce the Infinite Vocabulary Classifier, IVC. Our visual tokenizer generates discrete labels by quantizing residual features, predicting the labels for the next scale residual features and minimizing the target using cross-entropy loss. Previous methods directly predicted these index labels with a classifier that had a fixed number of classes, which led to high computational costs and unclear supervision. We utilize a bitwise VQVAE as our visual tokenizer, allowing for a very large vocabulary size. For instance, with a vocabulary size of 2 raised to the power of 32 and a height of 2048, a traditional classifier would require an enormous weight matrix with trillions of parameters, far beyond current computational capabilities. Additionally, VQVAE uses a sign function during quantization. The positive elements are multiplied by their corresponding base and summed to produce the index label. This quantization method means that small changes in near-zero features can lead to significant label changes, making it hard for conventional classifiers to optimize. To solve these computational and optimization issues, we propose the IVC, which uses multiple binary classifiers in parallel to determine if the next scale residual is positive or negative, significantly reducing memory and parameter requirements. For example, with a vocabulary size of 2 raised to the power of 16 and a height of 2048, we save nearly all parameters and GPU memory. Moreover, when there are near-zero values that confuse the model, supervision in other dimensions remains clear, making the IVC easier to optimize compared to traditional classifiers. Next, we address the weaknesses of teacher forcing training, which we inherit from large language models, LLMs. In visual tasks, predicting the next scale residuals differs from predicting the next token in language, as we cannot fully decode an image until we have all residuals. We find that teacher forcing leads to significant discrepancies between training and testing, as it only refines features at each scale without correcting earlier mistakes. These errors can accumulate and distort the final generated images. To tackle this, we introduce bitwise self-correction, BSC. We create a flipped version of the residuals by randomly altering bits, simulating different error strengths. This flipped residual contains errors, while the original does not. By replacing the original with the flipped version for predictions, we recompute the input and perform requantization to obtain a new target. This process is efficient, as it does not add computational costs or disrupt parallel training. Each scale undergoes random flipping and requantization, allowing the model to correct previous errors and reducing the discrepancies caused by teacher forcing. Finally, we discuss how Infinity can generate realistic images with various aspect ratios, unlike previous models that only produced square images. The challenges include defining the height and width of the residuals based on different aspect ratios and designing a positional encoding method that accommodates various scales. We predefine a list of scales for each aspect ratio, ensuring that the aspect ratios are consistent, especially in later predictions. We also maintain similar areas for different aspect ratios at the same scale to keep training sequence lengths comparable. To address the positional encoding challenge, we apply a resolution-aware method that preserves the 2D structure of images and use learnable scale embeddings to differentiate features across scales. This approach is more efficient than previous methods, requiring fewer parameters and adapting better to varying sequence lengths. Section Summary. In this section, we introduce the Infinite Vocabulary Classifier, IVC, which utilizes multiple binary classifiers to efficiently predict residual features, significantly reducing computational costs and improving optimization compared to traditional classifiers. We also propose bitwise self-correction, BSC, to mitigate train test discrepancies caused by teacher forcing training, enabling our model to correct prediction errors dynamically, and we address the challenges of generating images with varying aspect ratios through a carefully designed scale schedule and resolution-aware positional encoding. Section: Dataset. In this section, we describe our dataset and implementation process. We curated a large dataset from open-source academic sources and high-quality internal data. Our pre-training dataset includes cleaned academic datasets like LAION, COYO, and OpenImages. We used an OCR model and a watermark detection model to remove images with excessive text or watermarks. Additionally, we applied Aesthetic v2 to filter out images with low aesthetic quality. For implementation, we redefined text-to-image generation as a task that progresses from coarse to fine predictions. We trained our model, Infinity, which has 2 billion parameters, in stages. Initially, we trained it on the pre-training dataset at a resolution of 256 for 150,000 iterations, using a batch size of 4096 and a learning rate of 0.00006. We then increased the resolution to 512 and trained for 110,000 iterations with the same settings. Finally, we fine-tuned Infinity at a resolution of 1024 using a smaller, high-quality dataset for 60,000 iterations, with a batch size of 2048 and a learning rate of 0.00002. Throughout all training stages, we used images with various aspect ratios. For evaluation, we reported results on well-known benchmarks like GenEval and DPG, and we also assessed our method using 2 human preference benchmarks, Image Reward and HPSV 2.1, which predict human preference scores based on numerous ranked text-image pairs. We created a validation set of 40,000 text-image pairs to measure FID. In terms of qualitative results, we showcased images generated by our Infinity 2B model, demonstrating its ability to produce high-quality images across different categories based on user prompts. We provided examples that highlight Infinity's strong prompt following capabilities, showing that it adheres to both short and long prompts. We believe these improvements stem from our bitwise token prediction and scaling autoregressive modeling. Infinity also effectively renders text according to user specifications, accurately reflecting various fonts, styles, and colors across different backgrounds. In benchmark evaluations, our model achieved the highest overall score of 0.73 on GenEval and a reasoning score of 0.49. On DPG, we reached an overall score of 83.46, outperforming other models like SDXL and DALL-E 3, and achieved the best relation score of 90.76 among open-source text-to-image models. In human preference evaluations, our results showed that Infinity was more frequently chosen by participants for its overall quality, prompt adherence, and visual appeal compared to other models. We also noted that Infinity excelled in both image reward and HPSV 2.1 benchmarks, indicating its ability to generate more appealing images. Regarding inference latency, Infinity demonstrated a significant speed advantage over diffusion models, achieving 7 times faster inference compared to SD 3.5 at the same parameter size. We also explored scaling the vocabulary of our visual tokenizer. By increasing the vocabulary size, we improved the performance of our discrete VQVAE, matching that of continuous models. We observed consistent improvements in RFID as we scaled the vocabulary from 65,536 to 18,446,744,709,551,616. Our discrete tokenizer achieved an RFID of 0.61 on ImageNet at a resolution of 256 by 256 when the vocabulary size was 4,294,967,296, surpassing the continuous VAE of SD. Finally, we compared our infinite vocabulary classifier, IVC, with a conventional classifier under a smaller vocabulary size. Our evaluations showed that IVC resulted in lower reconstruction loss and FID, indicating better fitting capabilities. Training Infinity with IVC also produced images with richer details, aligning with higher image reward scores. Section Summary. In this section, we curated a large-scale dataset from open-source academic sources and employed various filtering techniques to enhance image quality before training our model, Infinity, using a progressive strategy across different resolutions. Our evaluations demonstrate that Infinity excels in generating high-fidelity images, adhering to user prompts, and achieving superior performance in human preference assessments compared to other text-to-image models. Section: Scaling Bitwise AutoRegressive Modeling. In this section, we explore the benefits of scaling Bitwise AutoRegressive Modeling. We increase the vocabulary size to 2 raised to the 32nd power during the training of the T2I model, which is significantly larger than the int32 data type and can be viewed as virtually limitless. Our findings, illustrated in a figure, show that for smaller models, 125 million and 361 million parameters, a vocabulary size of 2 raised to the 16th power converges more quickly and yields better results. However, when we scale up to 2.2 billion parameters, the larger vocabulary of 2 raised to the 32nd power outperforms the smaller one after 40,000 iterations. This indicates that increasing the vocabulary size is beneficial as we scale up the model. We also examine how scaling up the transformer impacts generation. In another figure, we present the validation loss in relation to total training iterations and computational floating point operations for various sizes of the Infinity model. We consistently observe that as we increase training steps and computational resources, the validation loss decreases. However, the benefits of training smaller models for longer periods do not match those of training larger models for shorter times. This trend mirrors findings in language models, suggesting that increasing model sizes with proper training is promising. To quantify the relationship between validation loss and evaluation metrics, we calculate Pearson correlation coefficients through linear regression. The coefficients for GenEval, image reward, and HPSV2 are very close to -1, indicating a strong linear correlation as we scale model sizes from 125 million to 4.7 billion parameters. This encourages us to further scale up Infinity for improved performance. We also visualize the scaling effects by comparing generated images of 3 model sizes, 125 million, 940 million, and 4.7 billion, across 3 different training schedules, 10,000, 40,000, and 90,000 iterations. The quality and semantics of the images improve as we increase model size and training compute, consistent with Infinity's scaling behavior. Next, we discuss bitwise self-correction, We present evaluation metrics and images generated by models trained with teacher forcing and bitwise self-correction methods. We observe significant advantages from bitwise self-correction, which primarily stems from its self-correction mechanism rather than random flipping. Self-correction mimics prediction errors and re-quantifies them for correction, which is crucial for autoregressive T2I models as it helps reduce discrepancies between training and testing. In our ablation studies, we investigate the optimal strength for bitwise self-correction. We find that weak imitation of mistakes does not fully utilize the potential of this method, while random flipping of 30% of bits yields the best results. Regarding positional embedding, we note that learnable absolute positional embeddings introduce too many parameters and can become confused with varying sequence lengths. Since sequence lengths change frequently during training with different aspect ratios, we apply a method called Rope 2D along with learnable scale embeddings. Rope 2D maintains the 2D structure of images, while learnable scale embeddings help differentiate features across various scales. Our comparisons show that this approach converges faster and achieves higher training accuracy than using learnable absolute positional embeddings. Finally, we emphasize the importance of decoding for enhancing generation quality. We implement pyramid classifier-free guidance, where the strength of guidance increases linearly as the scale progresses. This approach addresses the issue of model collapse when applying large guidance values at early scales. We find that Infinity can handle large guidance values even at early scales, especially with bitwise self-correction. We revisit different decoding methods and identify the most effective one, visualizing the results in a figure, which leads to the best generation outcomes.